Last of Newton's laws of motion is the third law, also known as the action-reaction law, that says this: for every action force, there is always an equal and opposite reaction force. This is a simplified version of it. There's a little bit more for you to know about this. And these are the things. These two forces, the action and the reaction force, they need to act on the same line of action. They need to be collinear, all right? They have to be acting on different objects. They cannot act on the same. They need to be of the same type. You cannot have like a frictional force on one side and an electrical force on the other. No, they have to be, in this case, both frictional or both electrical in nature. They have to have the same magnitude, the same size, and they need to have opposite reactions. A few examples here. A book on top of a table. We are talking about two contact forces: the contact force of the book on the table and the contact force of the table on the book. A common mistake is to put the weight of the box as one of the forces and the contact force of the table on the book as the other, the reaction pair for that weight. No, because it violates this. They are not the same type. They are both contact forces. Now, if this is either stopped or moving at a constant speed, and since being a table, it's going to be stopped, the force that with which the book is in contact with the table is going to be equal in magnitude to the weight, but it is not the weight. I can go there already. The weight of an object, the reaction force of that weight, is on the center of the planet, the Earth in this case, pointing up. So, for example, my own weight down is balanced. The reaction force of my own weight is on the center of the Earth, pointing up. Now, it's obviously the Earth that pulls me down, and I know I'm not particularly on the light side, but I don't think I will ever pull the Earth up because of the difference of masses. It's going to be the same. The ratio of the difference of masses between me and the Earth is the same as the ratio of the accelerations with which the Earth pulls me down and the one with I pull the Earth up. So you can see here that I will always be the one being pulled down and not the other way around. In the case of a pistol shooting a bullet, the moment the pistol makes its force on the bullet for the bullet to go out of it, you will know that there will always be a push of the pistol in the opposite direction, and this is caused by, again, a contact force of the bullet on the pistol. Since the mass of the bullet is much smaller than the pistol associated with the body connected to it, it's the bullet that goes that way and not with a high speed, and not the pistol that goes that way with the same speed. All right. Again, the ratio of the accelerations is the same as the ratio of the forces. What if you have connected objects? When you have connected objects, this is a particular class of questions that you're going to find in exams. Most of them are going to be about pulleys, but here I use the example of a car pulling a caravan. All right? Things that you need to know. Let's say that the car and caravan, they are accelerating in that direction. So if they are connected, the acceleration of this car is going to be the same as the acceleration of the caravan. It doesn't make sense that this accelerates at a different rate than this. Otherwise, they will not be connected, right? And more things to know. What is the force that binds one object to the other? In this case, is going to be a tension, all right? Between this metallic thing that connects the two vehicles, there is a tension there, all right? And these are going to be, they are of the same kind. They have opposite directions. They have equal magnitudes. That's very important. And they act in the same line of action. So they are the action-reaction pair. Okay? And another thing that you need to know is that for the purpose of solving exercises, sometimes it's convenient for you to think of this as a single object. And if you think of this as a single object, then these tensions are going to be interior or inside forces that you can neglect. You just consider this as a single object with a mass of this plus that, all right? And then the only forces acting on this object are going to be the force of the engine and the friction of the two vehicles. In this case, I didn't consider any for convenience for the purpose of what I'm explaining. I'm just considering the friction of the caravan and not the car. So in this case, if you consider this as a single object, the single object is going to have just that force and this force associated with it. Obviously, there's a weight and the reaction force, but I'm not considering them because the motion occurs in this x direction and not on the y direction. All right? So what do I mean with this, mathematically speaking? When you have connected objects, like I said, you can consider them as a single object, and then you can consider them individually. Let's look at this car A. What forces do you have connected to this or associated with this car A? Again, never mind the weight and the reaction force of the road on it. They are represented here in purple. So you have, for car A, the resultant force is going to be the mass of A times the acceleration. That's Newton's second law. So what is the resultant force? It's basically F minus TB, okay? TB is what I call the tension of B on the car, all right? The tension on the car caused by the caravan B, okay? So this minus this equals the mass of this times the acceleration. That's what I wrote over here, all right? Let's look now at B alone. What forces do you have associated with B? They are here in yellow. You have TA, which is the tension that you have here on the caravan caused by car A. And this is the force that actually makes B move in that direction. And then you have a friction. Like I said, the acceleration of B needs to be the same as A, right? So the resultant force of B is what? Is TA minus the friction, which equals the mass of B times the acceleration, right? Since these two tensions have the same magnitude, and I already put here the correct signs, the minuses here, so I can just call it T, all right? They have the same magnitude, I just call T, all right? So combining these two equations, I can get a general expression for this situation as a whole, all right? I combine these, I solve this for what? I solved the bottom one for T, I substituted it on top, see what I did? I put the friction to that side, so I have tension equals the friction plus MB times A. Then I put this result over there instead of T, that's what I did over here. Then I just got rid of the brackets, so the force minus the friction equals the mass of A plus the mass of B times the acceleration. What is this? This is what I said right at the beginning. This is what happens if you eliminate the tensions. This is what happens if you consider this as a single object. What do you have? You have that force minus this friction equals the total mass, MA plus MB, times the acceleration, which is the same for both. All right? By doing this, you eliminate the internal function, the internal forces of this object, and that's what you'll get in terms of a mathematical expression. All right? Let's look at pulleys now. This is very important because now the mental trick that you have to do is not thinking of directions in terms of up-down. All right? On a pulley, what happens? You have one object that goes down and another one that goes up because they are connected through a string. All right? You will also have tensions here. But now my advice to you is to think of the positive and the negative direction, not in terms of up-down, but in terms of the motion of the object. See here? In this case, I considered Since the motion is going to be like this one is heavier than that. So I consider everything that moves like this as being positive, and any force that points in the opposite direction of this as being negative. All right? This is crucial for you to understand what's going on. Actually, you don't have to do it this way, but this is the way that simplifies the calculations. All right? So again, all forces that contribute to this motion, so up in this case and down in that case, is positive. Any force that resists this motion, so any force that points down in this side and up in that side, is going to be negative. All right? So this motion over here is positive. This direction over here is negative. All right? That's what I wrote over here. And just like on a situation here in a car and a caravan, as long as you have a single string, on the same string, the tension is always the same in magnitude. Okay? The tension on a single string is always the same. And you consider it also as an internal force, like these two over here, if you look at the pulley as a single object. All right? So again, let's see what's going on. Just like an example of the car and the caravan, the acceleration with which this one goes down is the same as the acceleration with which this over here, this A, goes up, right? They are connected by a string. That's what you have over there. Let's now look at each one individually, okay? Let's look at A. Why is A going up in the perspective of A? What forces do you have associated with A? You have the tension and you have the weight of A. All right? So you know that the tension minus the weight equals the mass of A times the acceleration, right? What's happening with B? B is going down. Why? Because the weight of B minus the tension equals the mass of B times the acceleration, right? Don't forget that this acceleration and this acceleration, they are the same. As this one goes down, the other one goes up. You also need to understand one thing, and I urge you to do this in your diagrams, all right? If this is true, then this force needs to be bigger than that one, and this one needs to be bigger than that one, but these two need to be the same. So you have to make your sketch, I encourage you to make the sketch in a way that you put this arrow big enough and this arrow small enough so that this over here is somewhere in between. And this is clearly visible. Don't be shy. I see lots of students making tiny diagrams. No, but make it big enough so you can perceive what's going on. You look at this and all the physics associated with this situation, they are already there. All right? Usually when I have objects of different masses on a pulley, I tend to put the heavier one bigger, because this gives you already the perception of what is going to happen, which in this case is this one going up and that one going down. All right? So let's do some math over here. All right? So on A, what is going on over here? I work this out in terms, here I put the FG as MAG. Here I put the FG of B as MBG. All right? I work both in terms of the tension. So I have here an expression for the tension for A, here an expression for the tension for B. All right? Then I add the one and the other. All right? So what does this mean? I know that it stops here. So I stopped over here for me to have two expressions for T for each one of the objects. And then if I look at this and I add A and B, okay, what is going to happen? I eliminate T, and I know only that FG minus FG of B minus FG of A. So basically this minus this equals the sum of the masses times the acceleration. This is a result similar to this one over here. All right? If you look at this as a single object, again, adding those two, I eliminate the tensions. So the tensions are going to be inside forces for this object as a whole. And the only forces that you have to worry about are the weights. All right. So the weight of this minus the weight of this. Don't forget that this is going to be positive. This is negative. This contributes to this motion. This one doesn't. So one minus the other equals the mass of the object, which is m of a plus m of b, times the single acceleration that you have associated with this system. All right. Then I did a little bit more. I just expanded this, and you could have an expression like that. Then you just get whatever expression, mathematical expression you need to solve the question that you are being asked. But the physics associated with connected objects is always the same, regardless of you having something like this or something like this.